Earth's unique ability to support life starts with its location in the solar system, often referred to as the Goldilocks Zone or the habitable zone. This chapter explores how Earth's position relative to the Sun is neither too hot nor too cold, providing the perfect conditions for liquid water and a stable climate, both crucial for sustaining life. The Goldilocks principle is central to understanding why Earth can support life. In astronomy, the habitable zone is the region around a star where the temperature is just right for liquid water to exist on a planet's surface. Earth lies comfortably within this zone, unlike Venus, which is too close to the Sun and therefore too hot, or Mars, which is too far away and too cold. The distance between Earth and the Sun, approximately 93 million miles, 150 million kilometers, ensures that our planet receives the right amount of solar energy. This energy drives the weather, climate, and ecosystems that are vital to life. If Earth were only a bit closer or farther from the Sun, these delicate systems would be thrown off balance, making the planet either too hot or too cold to sustain life as we know it. Earth's nearly circular orbit around the Sun ensures relatively consistent solar energy throughout the year. This stable orbit prevents extreme variations in temperature, which is crucial for maintaining a climate that supports diverse forms of life. Additionally, Earth's axial tilt of about 23.5 degrees plays a significant role in creating the seasons. This tilt allows for a range of climates and ecosystems, from tropical rainforests to polar ice caps, all of which contribute to Earth's biodiversity. The tilt also ensures that no region of Earth becomes too hot or too cold for extended periods, further stabilizing the planet's climate. In contrast, other planets in our solar system either orbit too close to or too far from the Sun to maintain conditions suitable for life. Venus, with its scorching surface temperatures caused by a runaway greenhouse effect, and Mars, with its thin atmosphere and freezing temperatures, illustrate how a planet's position can determine its habitability. Earth's fortunate placement in the habitable zone, combined with its stable orbit and axial tilt, creates the just right conditions necessary for life to flourish. These factors, along with the presence of liquid water and a protective atmosphere, make Earth the only known planet in our solar system capable of supporting life. Earth's atmosphere is more than just the air we breathe. It's a complex and dynamic shield that protects and sustains life on our planet. This chapter delves into the composition and structure of Earth's atmosphere, explaining how it creates a stable environment, shields life from harmful radiation, and plays a critical role in regulating the planet's climate. Earth's atmosphere is a mixture of gases, primarily nitrogen, 78%, and oxygen, 21%, with traces of argon, carbon dioxide, and other gases. This composition is unique among the planets in our solar system and is essential for life. Oxygen is crucial for respiration in animals and humans, while nitrogen plays a key role in the growth of plants through the nitrogen cycle. Carbon dioxide, though present in small amounts, is vital for photosynthesis, the process by which plants convert sunlight into energy, producing oxygen as a byproduct. This balanced composition of gases creates an environment where life can thrive. One of the most critical functions of Earth's atmosphere is its ability to shield life from the Sun's harmful ultraviolet, UV, radiation. The ozone layer, located in the stratosphere, absorbs and scatters the majority of UV rays, preventing them from reaching the Earth's surface where they could cause severe damage to living organisms. Without this protective layer, life on Earth would be exposed to high levels of UV radiation, leading to increased rates of skin cancer, cataracts, and other health issues in humans, as well as damaging the DNA of plants and animals. Earth's atmosphere also plays a vital role in regulating the planet's climate. The greenhouse effect, a natural process in which certain gases trap heat from the Sun, keeps Earth's surface warm enough to support life. While a certain level of greenhouse gases like carbon dioxide and methane is necessary to maintain this warmth, the delicate balance must be maintained. Too much can lead to global warming, while too little could plunge the planet into a deep freeze. The atmosphere's ability to circulate air and moisture through wind patterns and the water cycle further helps to distribute heat around the planet, creating a stable climate that supports diverse ecosystems. This balance is unique to Earth. Other planets, like Venus with its thick, heat-trapping atmosphere, or Mars with its thin, ineffective atmosphere, do not share these life-sustaining characteristics. Another crucial aspect of Earth's protection is its magnetic field, generated by the movement of molten iron in the planet's outer core. This magnetic field extends into space and forms the magnetosphere, which deflects harmful charged particles from the Sun, known as solar wind. Without this shield, these particles would strip away the atmosphere, as seen on Mars, making it impossible for Earth to retain the air and water necessary for life. Earth's atmosphere, with its life-sustaining composition, protective ozone layer, and climate-regulating properties, is a key factor that sets our planet apart from others in the solar system. Its unique characteristics not only support life but also protect it from the many dangers of space, making Earth the only known haven for life in our solar system. While Earth's atmosphere provides a vital shield against many of space's dangers, another critical protective layer lies in the planet's magnetic field. This invisible force, generated by the movement of molten iron within Earth's outer core, extends far into space and plays an essential role in safeguarding life on our planet. The magnetic field deflects solar wind, traps harmful radiation, and prevents the erosion of the atmosphere, all of which contribute to Earth's unique ability to support life. Earth's magnetic field is generated by the geodynamo, a process that occurs deep within the planet's core. The Earth's core is composed primarily of iron and nickel, with the outer core existing in a molten state. As the Earth rotates, the molten iron moves, creating electric currents that generate the magnetic field. This field extends from the Earth's interior out into space, forming the magnetosphere, a vast region that encircles the planet. The magnetic field has poles, much like a bar magnet, with a magnetic north and south. However, unlike a simple bar magnet, Earth's magnetic field is dynamic and complex. The poles are not fixed and can shift over time, a phenomenon known as geomagnetic reversal. While these reversals have occurred many times throughout Earth's history, the magnetic field itself has always provided a critical shield for the planet. The Sun emits a constant stream of charged particles known as the solar wind. This wind is composed of protons, electrons, and other particles traveling at high speeds, carrying energy from the Sun out into space. When these particles reach Earth, they encounter the planet's magnetic field, which acts as a protective barrier. The magnetosphere deflects the majority of the solar wind, preventing it from directly impacting the Earth's atmosphere and surface. Without this deflection, the solar wind could strip away the atmosphere, as it has on other planets like Mars. Mars, which has a very weak magnetic field, has lost much of its atmosphere over billions of years due to the relentless bombardment of solar wind. This loss has left the Martian surface exposed to harmful radiation and made it a much harsher environment, contributing to its inability to support life as we know it. The magnetosphere not only deflects solar wind but also traps some of the charged particles in regions known as the Van Allen radiation belts. These belts are layers of energetic particles held in place by Earth's magnetic field, encircling the planet like a protective barrier. While these particles are dangerous to humans and electronics in space, the Van Allen belts prevent them from reaching the Earth's surface, protecting life from high levels of radiation. While the magnetosphere protects Earth from the dangers of solar wind, it also creates one of the planet's most stunning natural phenomena, the auroras. When charged particles from the solar wind penetrate the magnetosphere, particularly near the magnetic poles, they collide with atoms in the Earth's atmosphere. These collisions excite the atoms, causing them to emit light and creating the vibrant displays known as the aurora borealis, northern lights, and aurora australis, southern lights. Auroras are not just beautiful, they are a visible manifestation of Earth's magnetic field at work. The lights dance across the sky in patterns that reflect the interaction between the solar wind and the magnetosphere, reminding us of the constant cosmic battle taking place above our heads, and the invisible shield that protects us. Beyond deflecting solar wind and creating auroras, Earth's magnetic field plays a crucial role in preserving the planet's atmosphere. As previously mentioned, the solar wind has the potential to strip away a planet's atmosphere over time. Earth's magnetosphere, however, prevents this by diverting the flow of solar particles around the planet. This protection has been essential for maintaining Earth's atmosphere over billions of years. The atmosphere not only provides air for breathing but also regulates temperature, distributes water, and shields the surface from harmful radiation. The continued existence of this atmosphere is one of the reasons Earth remains habitable, while other planets, like Mars, have lost much of theirs, leading to harsh and life-prohibiting conditions. The magnetic field also protects Earth from cosmic rays, high-energy particles from outside the solar system. These rays can be damaging to living organisms, causing mutations and other harmful effects. Earth's magnetic field deflects many of these particles, reducing the amount of cosmic radiation that reaches the surface. This further contributes to the safety and stability of life on our planet. When we compare Earth's magnetic field to those of other planets in the solar system, the uniqueness of our planet's protective shield becomes evident. Venus, for instance, lacks a significant magnetic field, leaving it vulnerable to solar wind. This exposure has contributed to the extreme conditions on Venus, including the loss of any potential water and a runaway greenhouse effect that has made the planet inhospitable. Mars, as mentioned earlier, has only a weak magnetic field, which has allowed much of its atmosphere to be stripped away. The thin Martian atmosphere offers little protection from solar and cosmic radiation, creating an environment hostile to life. Jupiter and Saturn, on the other hand, have extremely powerful magnetic fields, much stronger than Earth's. However, these gas giants are composed primarily of hydrogen and helium, lacking a solid surface where life could exist. While their magnetic fields protect them from solar wind, these planets do not have the necessary conditions, such as liquid water and a stable atmosphere, to support life as we know it. Earth's magnetic field, therefore, stands out as uniquely suited to supporting life. It is strong enough to protect the planet from harmful radiation and atmospheric erosion, yet it exists alongside the other conditions necessary for life: liquid water, a stable climate, and a rich atmosphere. While Earth's magnetic field has been a stable and protective force for billions of years, it is not immune to change. Geomagnetic reversals, where the magnetic poles flip, have occurred throughout Earth's history. These reversals can weaken the magnetic field temporarily, potentially increasing the planet's exposure to solar and cosmic radiation. However, life on Earth has survived these reversals in the past, suggesting that the magnetic field, even when weakened, continues to provide significant protection. Current research also indicates that Earth's magnetic field is slowly weakening, a trend that may be part of a natural cycle leading up to a future reversal. Scientists are closely monitoring this weakening to understand its potential impacts on technology and life. However, even with this weakening, Earth's magnetic field remains a critical shield, one that has played an essential role in making our planet the only known haven for life in the solar system. Water is often considered the essence of life, and Earth's abundance of liquid water is one of the most critical factors that sets our planet apart from others in the solar system. Covering over 70% of the Earth's surface, water is not only vital for all known life forms but also plays a key role in shaping the planet's environment, weather patterns, and geological processes. In this chapter, we will explore why liquid water is so essential for life, how it exists on Earth in such large quantities, and why other planets in our solar system lack this precious resource. Water's importance to life lies in its unique physical and chemical properties. It is the only substance that exists naturally in three states: solid, ice, liquid, and gas, water vapor, under the temperature and pressure conditions found on Earth. This versatility allows water to participate in a wide range of biological and geological processes. One of the most remarkable properties of water is its ability to dissolve a vast array of substances, earning it the title of the universal solvent. This property is crucial for life because it allows water to carry nutrients, oxygen, and waste products in and out of cells. The ability of water to dissolve salts, minerals, and organic compounds also plays a fundamental role in biochemical reactions, making it indispensable for the chemistry of life. Water also has a high specific heat capacity, meaning it can absorb and release large amounts of heat with only a small change in temperature. This property helps stabilize Earth's climate by buffering temperature fluctuations, ensuring that the planet's surface remains within a range that is conducive to life. Oceans, rivers, and lakes act as heat reservoirs, moderating the effects of solar radiation and maintaining a relatively stable environment for living organisms. Another vital property of water is its high surface tension, which allows it to form droplets and flow through narrow spaces. This is essential for the movement of water through soil, plants, and the vascular systems of animals. Water's surface tension also plays a role in the formation of clouds and precipitation, which are critical components of Earth's water cycle. The continuous movement of water through the Earth's atmosphere, surface, and underground is known as the water cycle, or hydrological cycle. This cycle is essential for distributing water across the planet, ensuring that life can thrive in diverse environments. The water cycle involves several key processes: evaporation, condensation, precipitation, infiltration, and runoff. Evaporation occurs when water from oceans, lakes, rivers, and the land surface is heated by the sun and transformed into water vapor. This vapor rises into the atmosphere, where it cools and condenses into clouds. Condensation is the process by which water vapor in the atmosphere cools and changes back into liquid droplets, forming clouds. This step is crucial for the formation of precipitation. Precipitation occurs when these water droplets combine and grow large enough to fall back to Earth as rain, snow, sleet, or hail. Precipitation replenishes freshwater sources on land, such as rivers, lakes, and groundwater. Infiltration happens when precipitation seeps into the ground, replenishing aquifers and providing water for plant roots. Some of this water is absorbed by vegetation, while the rest contributes to groundwater reserves. Runoff is the movement of water over the land surface, eventually returning to oceans, rivers, and lakes. Runoff also carries nutrients, sediments, and minerals, which are essential for ecosystems and agriculture. The water cycle is a self-sustaining system driven by solar energy and gravity. It ensures that water is continuously recycled and distributed, providing life with a constant supply of this essential resource. Without the water cycle, Earth would quickly become barren and inhospitable, as water would be unevenly distributed and unavailable to many regions. Water is not only essential for biological processes but also plays a significant role in shaping the Earth's landscape through geological processes. One of the most important of these processes is erosion, where water, in the form of rivers, rain, and waves, wears down rocks and soil, transporting sediments and reshaping the land. Over millions of years, erosion by water has carved out valleys, canyons, and deltas, creating diverse habitats for life. Water also plays a critical role in the formation of sedimentary rocks, which are created by the accumulation and compaction of sediments over time. These rocks often contain fossils, providing a record of past life and helping scientists understand Earth's history. Additionally, water is involved in the process of plate tectonics, as it facilitates the movement of Earth's crustal plates. The presence of water in subducting oceanic plates lowers the melting point of rocks, leading to the formation of magma and the occurrence of volcanic activity. This activity, in turn, plays a role in the recycling of Earth's crust and the release of gases that contribute to the atmosphere. One of the great mysteries of our solar system is why Earth has abundant liquid water, while other planets do not. Several factors contribute to Earth's ability to sustain liquid water, including its distance from the Sun, its atmospheric composition, and its geological activity. Distance from the Sun. Earth is located in the habitable zone, often referred to as the Goldilocks Zone, where temperatures are just right for liquid water to exist. If Earth were closer to the Sun, like Venus, it would be too hot, causing water to evaporate and be lost to space. If it were farther away, like Mars, it would be too cold, and water would exist only as ice. Atmospheric composition. Earth's atmosphere plays a crucial role in maintaining the right conditions for liquid water. The greenhouse effect, caused by gases like carbon dioxide and water vapor, traps heat and keeps the planet warm enough to sustain liquid water. Without this effect, Earth would be too cold, and water would freeze. Geological activity. Earth's active geology, driven by plate tectonics, helps maintain the planet's water supply. Volcanic activity releases water vapor and other gases into the atmosphere, contributing to the water cycle. Subduction zones recycle water back into the mantle, where it can be released again through volcanic eruptions. This continuous recycling of water ensures that Earth's surface remains wet. In contrast, Venus and Mars lack the conditions necessary to support liquid water. Venus's proximity to the Sun has caused a runaway greenhouse effect, leading to extreme surface temperatures that prevent liquid water from existing. Mars, on the other hand, is too cold and has a thin atmosphere, causing any water that once existed on the surface to either freeze or evaporate into space. While there is evidence that both Venus and Mars may have had liquid water in the past, the current conditions make it impossible for water to exist in liquid form for any extended period. The presence of liquid water is one of the primary criteria scientists use when searching for life beyond Earth. As a result, much of the exploration of our solar system has focused on finding evidence of water on other planets and moons. For example, missions to Mars have discovered signs of ancient river valleys, lake beds, and mineral deposits that suggest liquid water once flowed on the planet's surface. Additionally, the discovery of subsurface ice and seasonal flows of briny water on Mars has fueled speculation that some form of microbial life could exist there. Jupiter's moon Europa and Saturn's moon Enceladus are also of great interest because they are believed to have subsurface oceans beneath their icy crusts. These oceans, kept warm by tidal forces from their parent planets, could potentially harbor life. The discovery of plumes of water vapor erupting from Enceladus and signs of a subsurface ocean on Europa have made these moons prime targets for future missions aimed at searching for signs of life. However, despite these intriguing findings, Earth remains the only known planet in the solar system with stable, long-term bodies of liquid water on its surface. This unique feature is a key reason why Earth is the only known planet that supports life as we know it. Earth's ability to support life is not just a result of its physical properties, such as its atmosphere, magnetic field, or abundant water. The planet's biosphere, its complex web of life, interacting with and influencing the environment, plays a crucial role in maintaining the delicate balance that allows life to thrive. This chapter explores the intricate relationships within Earth's biosphere, how these interactions have evolved over billions of years, and why such a balanced system does not exist on other planets in our solar system. The biosphere is the global sum of all ecosystems, encompassing all living organisms and the environments in which they live. It includes the lithosphere, land, hydrosphere, water, and atmosphere, air, all interacting with one another to create a stable environment capable of sustaining life. The origins of Earth's biosphere date back more than 3.5 billion years, when simple life forms first emerged in Earth's primordial oceans. The early biosphere consisted of microorganisms, such as bacteria and archaea, which played a crucial role in shaping the planet's environment. Through processes like photosynthesis and chemosynthesis, these organisms began to convert sunlight and chemical energy into organic matter, producing oxygen as a byproduct. This gradual accumulation of oxygen in the atmosphere, known as the Great Oxidation Event, was a turning point in Earth's history, leading to the development of more complex life forms and the eventual rise of the rich diversity of life we see today. One of the most critical processes within the biosphere is photosynthesis, the process by which plants, algae, and certain bacteria convert sunlight into chemical energy, producing oxygen as a byproduct. Photosynthesis not only provides the energy that drives most ecosystems but also plays a vital role in regulating the Earth's atmosphere. During photosynthesis, plants absorb carbon dioxide from the atmosphere and use sunlight to convert it into glucose, a form of stored energy. In the process, oxygen is released into the atmosphere. This oxygen is essential for the survival of aerobic organisms, including humans, and helps maintain the balance of gases in the atmosphere. The importance of photosynthesis extends beyond its role in providing energy and oxygen. It is also a critical component of the carbon cycle, a process that regulates the levels of carbon dioxide in the atmosphere. By absorbing carbon dioxide, plants help mitigate the greenhouse effect, preventing the Earth from becoming too warm. This balance between carbon dioxide and oxygen is essential for maintaining a stable climate, which is one of the key factors that make Earth habitable. Earth's biosphere is characterized by a remarkable level of interconnectedness. All living organisms, from the smallest microorganisms to the largest mammals, are part of a vast and complex web of interactions. These interactions occur within ecosystems, where different species coexist, compete, and cooperate in a delicate balance that sustains life. Ecosystems are communities of living organisms interacting with their physical environment. They can vary in size from small ponds to vast forests, and they include both terrestrial and aquatic environments. Each ecosystem is composed of producers, such as plants, consumers, such as herbivores and carnivores, and decomposers, such as fungi and bacteria, that recycle nutrients back into the environment. Biodiversity, the variety of life in all its forms, is a key feature of healthy ecosystems. High levels of biodiversity contribute to the resilience of ecosystems, allowing them to withstand environmental changes and recover from disturbances. This diversity also ensures that ecosystems can provide essential services, such as pollination, nutrient cycling, and climate regulation, which are vital for life on Earth. The loss of biodiversity, often due to human activities such as deforestation, pollution, and climate change, can have severe consequences for ecosystems and the biosphere as a whole. Reduced biodiversity can lead to the collapse of ecosystems, making it more difficult for the planet to sustain life. Preserving biodiversity is therefore critical for maintaining the balance of Earth's biosphere. The Gaia hypothesis, proposed by scientist James Lovelock in the 1970s, offers a compelling perspective on the biosphere. According to this hypothesis, Earth and its biosphere function as a self-regulating system, where living organisms interact with their environment to maintain conditions that are favorable for life. The Gaia hypothesis suggests that life on Earth has actively shaped the planet's environment over billions of years, creating a stable climate, maintaining the balance of gases in the atmosphere, and regulating the chemical composition of the oceans and soils. For example, the production of oxygen by photosynthetic organisms has helped maintain an atmosphere suitable for aerobic life, while the carbon cycle has prevented the Earth from becoming too hot or too cold. While the Gaia hypothesis is a metaphorical way of understanding the complex interactions within the biosphere, it highlights the remarkable ability of life on Earth to maintain the conditions necessary for its own survival. This self-regulating system is one of the reasons why Earth has remained habitable for billions of years, despite changes in solar radiation, volcanic activity, and other external factors. The complexity and balance of Earth's biosphere are unmatched in our solar system. Other planets and moons lack the combination of factors necessary to support such a rich and interconnected web of life. There are several reasons why Earth's biosphere is unique. Lack of liquid water. As discussed in Chapter 4, liquid water is essential for life, and Earth is the only known planet in the solar system with abundant liquid water on its surface. Without water, the chemical reactions that sustain life cannot occur, and ecosystems cannot form. Extreme conditions. Other planets in the solar system experience extreme conditions that make life as we know it impossible. For example, Venus has surface temperatures hot enough to melt lead, while Mars has a thin atmosphere that offers little protection from solar radiation. These harsh environments prevent the development of complex ecosystems. Absence of a stable atmosphere. A stable atmosphere is crucial for regulating temperature, providing essential gases like oxygen and carbon dioxide, and protecting life from harmful radiation. Earth's atmosphere is uniquely suited to support life, while other planets, such as Mars and Venus, either lack a substantial atmosphere or have an atmosphere composed of gases that are toxic to life. No active biosphere. While some moons, like Europa and Enceladus, may have subsurface oceans that could potentially harbor microbial life, there is no evidence of a biosphere as complex and interconnected as Earth's. These moons lack the conditions necessary for the development of diverse ecosystems, and any life that may exist is likely to be limited to simple, isolated organisms. Despite its remarkable ability to sustain life, Earth's biosphere is not invulnerable. Human activities have placed unprecedented stress on the planet's ecosystems, leading to deforestation, pollution, climate change, and mass extinctions. These impacts threaten the delicate balance that has allowed life to thrive on Earth for billions of years. Climate change, driven by the increased concentration of greenhouse gases in the atmosphere, is one of the most significant threats to the biosphere. Rising temperatures, changing precipitation patterns, and more frequent extreme weather events are disrupting ecosystems and threatening biodiversity. The loss of habitats, such as coral reefs and rainforests, is leading to the extinction of species at an alarming rate. The depletion of natural resources, such as fresh water and arable land, also poses a challenge to the biosphere's ability to sustain human populations. Unsustainable agricultural practices, overfishing, and pollution are degrading ecosystems and reducing the availability of essential resources. Protecting Earth's biosphere is crucial for the survival of life on our planet. This requires global cooperation to reduce greenhouse gas emissions, conserve biodiversity, and promote sustainable practices that minimize environmental impact. By understanding the interconnectedness of life and the importance of maintaining balance within the biosphere, humanity can work towards a future where Earth remains a haven for life.